0.
Greetings and welcome, friends. Mr. Waddy here. Today we're talking about similarity and transformation, something that we've all been thinking about. I know you have not been able to wait until this lesson. This is the final lesson of Chapter 4 as well, by the way. It's 4.6 in your Big Ideas Geometry book. Man, geometry. Good times. Good times. Are you guys loving it? I'm loving it. Yeah, no promotions for my YouTube channel officially. That was completely spontaneous. So let's see. Performing similarity transformations. A dilation is a transformation that preserves shape but not size. So a dilation is a non-rigid motion, right? The result is non-congruent to the original. However, it is similar. A similarity transformation is a dilation or composition of rigid motions and dilations. Okay, so kind of like a composition of transformations that we've talked about in the past. So it says this: two geometric figures are similar figures if and only if, biconditional statement right there, there is a similarity transformation that maps one of the figures onto the other. Similar figures have the same shape, but not necessarily the same size. Necessarily. So that would suggest to me that congruent figures are similar, but not all similar figures are congruent. Wow. Congruence transformations preserve length and angle measures, while scale factor of a dilation is not equal to 1 or -1. Similarity transformations preserve angle measure only, and our side length has then been multiplied by our scale factor. Yes, very good. So let's do an example here. Example 1. Let's perform a similarity transformation. This is going to be so great. I think I've given you guys a little grid to work with. It's going to be amazing. Example 1, performing a similarity transformation. Graph ABC. Guys, we're so good at plotting points, aren't we? We're like the best we've ever been. We're the best there never was. 1, 2, 3, 4. To the left, up 1. There's A right there. Man, I'm plotting these points. -2, left 2, up 2. There's my B right there. And C, -2, 1. Wow, my graph is way bigger than it needs to be. Looks like I got a little right triangle here. It's adorable. There we go. I love it. I love it. Translation. So first thing we're going to do is translate. I'll use naranja for this halfway through the transformation thing. So we're going to translate by moving it 5 to the right and up 1. So A is now 1, 2, I lost count, 3, 4, 5, and then up 1. So here's my A prime. A prime, right? Let's see, C prime would be over 5, 1, 2, 3, 4, 5, and up 1. There is my C prime. And B prime, I could go 5 to the right and up 1, or I just noticed that B was 1 above C, so B prime must be 1 above C prime if that was a rigid transformation, which it was because that was a translation. All right. Could someone write this vector in component form for me, by the way, if I was thinking about it as a vector?
5, 1.
5, 1, yeah, bam. That's a skill that shows up on the test tomorrow. You are ready. Excellent. Let's see, dilation now. Let's scale this up, friends. We're going to now double the x's and the y's. So let's see, A is currently at 1, 2. So now it should be at 2, 4. Is that proper? I think so. Right. If I double each of its coordinates, so here's A double prime. C prime was at 3, 2, so C double prime will be at 6, 4. C double prime. I love it. And B prime was at 3, 3, so double it. Looks like 6, 6. Repew. And Ripapatow. There we go. There's my B double primes at. And I'll try to draw a little, let's see. That looks good enough. Yeah. Yeah. And so my result, my image to the pre-image and the pre-image's image ends up being twice the size linearly, but it is completely similar. All of these angle measures were preserved. So notice the angle at C double prime is still a right angle. It didn't somehow get doubled and become a 180 degree angle. That would have been weird. So angle measures are the same, but notice that the distance from B prime to C prime is 2, or sorry, B double prime, C double prime is 2, where the other cases they were only 1. So it's doubled the linear dimensions and it has quadrupled the area, right? We remember that trick? Man, you guys are going to be so set up for success when we teach that lesson one time in the future. It'll be great. Let's see. Here's a monitoring progress right here. Pow. Here, we'll just try one more of these. Ooh, this one's got a rotation and a dilation. This is actually a great last section because it's like combining all of our previous skills from earlier on in the chapter. And this is just like the boss fight where now we got to use all the things we learned. It's almost like the end of Avatar: The Last Airbender when he's like mastered all the elements. No, I don't know. And then he's like, he's got all of them now. And then like, oh man. Also, my 5-year-old son just started watching that show again, and I'm so pumped. So pumped. I don't know if you're being sarcastic about how cool my family is. I can't tell.
I'm not gonna put.
Oh yeah, the movie? No, I'm talking about the cartoon Nickelodeon, my friends. Oh yeah. Let's see. Let's plot this. -2, 2. There's C. And let's see, for D, I've got 2, 2, over 2, up 2 for my D there. Right there. Look at that. Gorgeous little segment. Ah, it's adorable. And let's see, I'm going to rotate 90 degrees about the origin question. Clockwise or counterclockwise? Counterclockwise. So C, when rotated 90 degrees, will be now here as C prime. Right? And D, 90 degrees this way, happens to actually land right on the old C spot there. There's D prime. All right? That was a rigid transformation. Rotations, they're cool. They are rigid. However, dilations, we are going to scale this, friends. And let's see. So C prime is at -2, -2. Let's half each of those coordinates. So the scale factor is 1/2, 1 to 2. So half of -2 is -1, half of -2 is -1. And notice that it's halfway to the origin from where it used to be. So there's my C double prime. And similarly for D double prime, it's going to be half of -2 is -1 and half of +2 is 1. So there's my D double prime right there. And it has lost its congruence, but it is similar. I guess I can't describe those angles because it didn't have any angles. But if it did, I'm just thinking of like the world's most interesting man now. I don't always have angles, but when I do and I go through a similarity transformation, my angles are still congruent. Classic. Am I right? Mm-hmm. Let's take a look at this one. I love these. These are like little mysteries. It's like, who done it right here? What happened? Someone changed my trapezoid, right? What happened here, guys? I've got to solve this mystery. Oh man, describe a similarity transformation that maps trapezoid PQRS, so that's the bigger one, to trapezoid WXYZ. All right. Does someone have a guess? Let's see. What do you think? I don't know. Any ideas?
Well, got flipped.
It got flipped. What are you thinking, Josh?
Reflected and dilated.
All right. It looks like step 1, there was a reflection. This would not necessarily be the only process. Reflection over what line?
Y.
The y-axis, yep. Okay, so a reflection that would have landed, I'll draw it just so we've got an idea, although it didn't ask us to. No, man, all right, nope. And let's see, there's Q, and then this one was 6 away, so 6 away over here. There's that, and then down there with the that and the that. And now how could I get this yellow shape down to that purple shape? It's a dilation. Oh, how'd you guess that? Dilation, K is equal to, how do you know 1/3? Okay, so this had 3 and this had 1. I like that. Anyone notice another way to recognize it? I was looking here. This distance to R prime was 3, and this distance to Y was 1. So it's 1 to 3 ratio, right? But I actually really like that spot right there, yeah. So 1/3, yeah. 1/3. Question, what's the area of this little purple guy compared to the yellow or orange guy?
6 times.
Oh, no.
8, 12, 7, 19.
1/9. It is 1/9 of the area.
What?
If the scale factor is 1/3, the ratio of the areas is 1/3 all squared, or 1/9.
You're saying a third of that little one?
I'm saying that 9 of these little ones would fit into that.
Prove it.
No, it's not part of today's lesson.
You're saying 1/9 of that huge one fits into that.
Ratio of areas. No, you guys can prove it. You can pause this video, take a screenshot, and then get your own writing tablet and your own YouTube channel and prove me right.
Or wrong.
Or wrong. Oh, or wrong. That's the challenge right there.
Wait.
I'm waiting.
Can we do like a negative reflection? That's like that. Or a negative dilation.
A negative dilation. Oh, we could have. Would that have helped? I don't think there's a way I could do that, because the negative dilation also like is a 180-degree rotation, right?
Yeah.
So then like there's a way that I could have gotten it there, but it would have been more than 2 steps. Here, we'll do one more of these just because there aren't that many examples today, and we like these. Let's see. Describe a similarity transformation that maps the following. Ooh, look at this lovely quadrilateral. Let's see. Quadrilateral. Let's see. I'm going to scale this up by a scale factor. Am I right, friends? Oh. Oh, man. I wouldn't have known how to do that without dilations either. It's not like I would have been able to use the computer to zoom in. So let's see. I'm mapping from the DEFG quadrilateral down to this little guy. Ooh, what is going on here?
Rotate on 80 degrees, then like brought that by half.
Okay, rotate hundo 80.
Yeah. 400 divided by.
All right, rotate hundo 80. So let's see. So G prime would have been here. F prime would have been all the way over here.
Oh, wait. What?
You're rotating 180, right? We're going from orange to purple.
Yes.
All right, let's see. Let's see. D over here is left 2 up 3, so right 2 down 3. That would have been the D. And then let's see, E was over 1 up 4, so let's go backwards 1 down 4.
Never mind.
No, I think you're onto something. All right. So step 1, you said rotate hundo 80 degrees. Okay, then what do you do? Let's see. To go from here to here, what's that difference? A full unit versus maybe that's a half unit? So is it a 1/2? No?
Go for it.
Let's see. Or this is 4 units away. This becomes 2 units away. Yeah, I think we dilate it where k is equal to a half.
Yeah. Oh my gosh, I was right.
Yeah.
Yeah.
Question: would alternative solution of this have worked? I'm sorry. Yeah, someone's saying it. Someone is, who said what? Dilate by what?
Negative one. Wait, what are we trying to do now?
Dilate by negative half.
We already solved the problem.
Yeah. Sometimes it's interesting to look at multiple solutions to see if one is more efficient and elegant.
How would you do that?
Ah, that's a question, my friend, right there.
Why is the first one K or the first one?
Sorry. All right, Aiden. What was your question? I'm sorry.
Why is the first one?
Why is this K what?
Why is that even relevant?
That's a K. It's just an ugly. It's an ugly K. All right. Thanks. But the good news is my family is cool. I think. I also can't tell. I don't know. But yeah, a negative scale factor results in a 180-degree rotation. It accomplishes the same thing. This is the same as that. Yeah. So yeah, if I half this and go in the opposite direction, I end up right there. Right. And if I half that and go in the opposite direction, I end up right there. All right. So yeah, those negative scale factors. Okay. So now I told you we were going to talk about proofs today. What? Man, I so wish I could just type. I should. Nah. I'll just write down some of my thoughts. All right, guys, here we go. Prove that 2 squares are similar.
They are because of the way it is.
They are because of the way it is.
I got 2 squares, so they're both squares. Because of that. Yes, sir.
We're going to prove this using magic. No, we're going to use Similarity Transformations, essentially. Okay, so guys, step 1. Imagine if I translate A to E. Yeah, he is a language specialist, right? Translate. Yeah. Bam. I'm picking up what you're dropping. Okay, so I translate it. I would have an image like this, somewhat. Yeah? You guys agree? All right. And let's see, this length is R. Now what could I do as my next step?
You could add a little curve in.
Oh, just like add a little curve, make it an S. Yep. I like that. That's done clever. I like it. All right. But I need to like scale that up. Perhaps I need to stretch it out proportionally. Dilate it is the word.
Wait, can we just say that like?
No? Yeah?
Wait. I get in general reading this. If you're thinking that it's similar, if it has all the same angles and similar, and all squares, that means they have all coordinates.
Yeah.
Then you don't need to do this. But they are both a square.
Yeah, it seems like you've got some additional information about squares and their angles. And yeah, I would agree. But yeah, we're talking about if I can find a way to translate this with a similarity translation that I know that they're similar because it's a non-rigid transformation, it would preserve the angles and the sides would be slightly different. But here's my question. What would K equal? And also, what is that letter?
S over R.
I think that's weirder than, yeah, I don't know.
I think it would be R over S, man.
A V and a C. I like it. R over S or S over R?
I don't know. That's over R.
It's the image over the pre-image. Image over the pre-image. So it's S over R. And then I would say something to the effect that since
Why is it S over R?
you do the image over the pre-image.
How do we know which one's the original?
Well, because I started over here, then I went to the green one, and now I'm trying to get it up to the big one. We were told they were squares.
What came first, the R and the S?
They were given simultaneously to us. So let's see. Since this is a similarity transformation, comma, and A, B, C, D mapped onto, let's see, I got to get the letters in the right order. E, F, G, H, the squares are similar. Right?
You're correct.
Yeah. You guys believe it? Do you believe it, friend? Let's see. I could give you one more. Nah. I think we're good. I want to get you guys some class quest time in. I want to get you some review time in, and you guys get the exclusive backstage pass to like Mr. Waddy Geometry Math Class Accelerated, whereas our internet friends don't. And if they ever wanted to be able to access this awesome live and in-person math lesson, they'd have to like move to this area, I guess, and like go to high school here, and maybe yeah, theoretically, if I raise enough money from my YouTube funds, buy a house in Brattleboro, raffle it off to one of my 111 or whatever subscribers, move them here from the Philippines, right? And then they get to take an actual math class with Mr. Waddy. A 1 in 8 chance because there's 8 teachers on the math department. Well, no, actually, if they took probability and statistics, they'd find out that if they take like 5 math classes, you would do what? 1/8 times 1/8 times 1/8 times 1/8 times 1/8, and then like subtract that or something. I don't know. We'd have to figure it out. I don't know. Go check out someone's probability channel. Have a good day, internet friends. There is no house that you're going to ever win from me. Bye-bye.